In this lecture, we are going to cover sections 10.4 through sections 10.6. First, we're going to discuss the dissociation of water. In chapter 10, we have observed water acting as a base and water also acting as an acid. Any molecule that is able to do that, it is known as amphoteric. So again, the definition of an amphoteric system is a molecule that can act as an acid or it can act as a base. So what does this mean? If we have a solution of pure water, these exchanges are going to happen very fast. So water can actually attack itself and act as an acid, but also act as a base. So that means that for very short periods of time, water is going to be forming hydronium ions and hydroxide ions. Now, you can see that this system is in equilibrium by the arrows that we have seen. So understand that having the presence of hydronium ions and hydroxide ions are going to tell if a particular solution is neutral, basic, or acidic. So all of the concepts that we are going to now explain came from the observation of the dissociation of water, but we are going to now focus more on the definition of what makes something have a pH. So in section 10.5, we are going to define what is the pH scale. So as you can see, by definition, the pH of a solution is used to indicate the acidity of a solution. Okay? More importantly, when it comes to this pH, it looks at what is the concentration of H plus, in other words, protons in the system. So anytime that we have something that it is acidic, is going to have a pH value that is less than 7. Anything that it is neutral is going to have a pH value at 7. And anything that is basic is going to have a value that is greater than 7. So what does that mean? Remember, acidity is related to the concentration of H+. So for an acidic solution, since the values are lower than 7, that means that when it comes to the concentration of H3O+ is going to be much higher than this value of 1 times 10 to the negative 7. When it comes to a neutral solution, understand that because the pH is at 7, the concentration of H3O+ equals that 1 times 10 to the negative 7. In that basic solution, because the pH value will be higher than 7, the concentration of H3O+ will be lower than 1 times 10 to the negative 7. For those of you that are like, where do we get these values? It has been observed experimentally that if you measure the concentrations of H3O+ and OH- in water at room temperature, so I'm just going to write that down. So at 25 degrees Celsius, the concentration of H3O+ in water is 1 times 10 to the negative 7 molar. The concentration of OH-, again, this is for water, is also 1 times 10 to the negative 7 molar. So that's where those numbers came from. Okay? Now, when it comes to pH, understand that there's different instruments that are utilized to measure pH. And on A, you can see that we have an electronic instrument. So that is a pH meter. We also have pH paper, and pH paper it has a dye that can perceive the concentration of H+, and according to that, it's going to change a different color. And also, there are natural dyes that are, for example, in fruit and vegetables that can turn different colors depending on the presence of H plus or protons in a particular solution. So C is actually purple cabbage. And this purple cabbage has a molecule that is called a flavin. And this flavin, depending on the type of solution that is exposed to, as you can see, it can give different colors. That you can actually find YouTube videos and even try it at home. So many common substances that we use in everyday life do have a pH value. That means that they will have a concentration of H plus in the solution itself. So as you can see, if we look at pH values, things like, I'm just going to zoom in. Lemon juice is acidic, soda is acidic, oranges are acidic, milk is a little bit on the acidic side, pure water is neutral, seawater is actually a little bit basic, ammonia, which it can be found in products like Windex, that tends to be basic, and even bleach, as you can see, has a basic pH. Now, when it comes to this, you guys need to learn how to calculate the pH of a solution, and that is given by the following equation. So one of the important equations that you guys need to know is that the pH equals the negative log of the concentration of hydronium. So understand that H3O plus, because this can act as an acid and donate a proton, is the same thing as when we ask for concentration of H plus. So understand that if you are given the concentration of H3O plus or H plus for a particular solution, you can calculate the pH directly. Two more important equations that you guys should know when you're doing these problems for the quizzes or for the exam is going to be, if I'm given the pH, how can I tell the concentration of H3O plus? So the concentration of H3O plus or H plus is going to be when you take the pH and you use it in the following equation. So every time you raise 10 to the negative pH is going to be giving you the concentration of H3O plus. And that's because in the first equation that we have for pH, that is log base 10. So that is equivalent. If we try to isolate H3O plus, you will convert that equation to equation number 2. Okay. So that is the second equation that you guys need to be familiar with. The third equation that you guys need to be familiar with is that when you multiply the concentration of H3O plus by the concentration of OH minus, let me just rewrite it a little bit below. The third equation is that the concentration of H3O plus times the concentration of OH minus, because we know the values for those two, is going to equal 1 times 10 to the negative 14 molar. Okay? So we are going to utilize these three equations that I just gave you guys for doing some problems that you guys need to be familiar with for quizzes and for exams. So as you can see, we are going to move on to part G in the worksheet. So I'm going to do specifically problems 1, 2, and 3. Okay? So problem 1 reads, if the H plus, and remember H plus is the same thing as saying H3O plus. If the H plus concentration is 2.1 times 10 to the negative 12 for perchloric acid, what is the pH? So when it comes to this, understand that because the question is asking for pH, we're going to be using the pH equation, okay? So pH equals the negative log of this value that we have, which is 2.1 times 10 to the negative 12 molar. And when you plug in that to your calculator, the value is 11.7. As you can see, the second question asks, is this solution acidic, basic, or neutral? If we review the concept that we just discussed, if anything is neutral, the pH is going to be equal to 7. If anything is basic, the pH is going to be larger than 7. And acidic means that the pH is going to be less than 7. So this solution, because it has a pH value of 11.7, that means that this is a basic solution. Number 2, calculate the pH if the OH concentration is 5.9 times 10 to the negative 1. Is this solution acidic, basic, or neutral? So understand that here we're still calculating pH, but so the problem doesn't give us H plus, but it gives us OH minus. So when it comes to this, understand that what is given is the concentration of OH minus. When the concentration of OH minus is what is given, then we need to use two equations. So, because we have OH concentration given and we need to calculate pH, you're going to first use the last equation followed by the first equation. So those are the two equations that we're going to utilize in this problem. So in the first equation, if we separate it to find the concentration of H plus, that means that 1.0 times 10 to the negative 14 molar over the concentration of OH minus can give us the concentration of H plus. So that means that if I use 1 times 10 to the negative 14 molar, or 1.0, I should say, and we divide it by the number given, 5.9 times 10 to the negative 1 molar, the result is going to be 1.69 times 10 to the negative 14 molar. I am not very strict when it comes to the sig figs and log. So in these problems, I will tell you how many sig figs you guys should be writing in, or the answer should have. So now that we calculated the concentration of H plus, the second step will be using that concentration of H plus to plug in into the pH equation to determine what is the pH of the solution. So the negative log of H plus is going to equal the negative log of what we found in result number 1, which is 1.69 times 10 to the negative 14 molar. When we put that in the calculator, understand that we get a result that is 13.8, and at a value of 13.8, that means that our solution is also basic. On the third problem that it says, what is the hydrogen ion concentration of a solution with pH 8.25? By looking at the pH value, we already know that this is a basic solution. So when it comes to this, if you're given the pH, then what you're going to be utilizing is that middle equation to determine the hydrogen ion or proton concentration. Remember that hydrogen ion is going to be the proton concentration, meaning concentration of H plus. And in this case, remember that equals the concentration of H3O plus. So for problem number 3, because it is given pH, I'm going to say H plus equals 10 to the negative 8.25. So the concentration of that H plus at a solution that has a pH of 8.25 is going to be 5.6 times 10 to the negative 9, and the unit for concentration is always molar. In section 10.6, we're going to specifically look at reactions of acids and bases. So for example, in your stomach, maybe you have heard that, oh, stomachs are very acidic. Well, understand that the gastric acid that is present in your stomach contains HCl and is produced, as you can see, by the cells that are in the stomach lining. So there are particular biochemical reasons why this occurs, and when we go into biochemistry, we are going to see why that is. When it comes to the reactions for acids and bases, the first one that we're going to be observing is how acids react with metals. Now, these reactions are not going to be far away from the different classifications that you guys learned in chapter 7. So, for example, acids are going to react with metals such as potassium, sodium, calcium, magnesium, aluminum, zinc, iron, or tin. When that happens, as you can see, you are going to be producing hydrogen gas and a salt. So if we look at the classifications that we've seen before, this is an example of a single replacement reaction. Acids also react with carbonates and bicarbonates. Now, in these systems, as you can see, you're going to be producing carbon dioxide, salt, and water. But as you can see in the bullet point, it says that when acid reacts with carbonates or hydrogen carbonates, we are going to be looking at this carbon dioxide, salt, and water, but this reaction may not be too familiar to you guys. So understand that these reactions are not combustion reactions. Because if you guys remember from when I explained this in chapter 7, combustion reactions is when we react something with just molecular oxygen. The presence of CO2 in water does not signify that we have a combustion reaction. The reason why we have this CO2 and water forming is because these reactions are double displacement reactions or double replacement reactions, followed by decomposition. What this means is that this CO2 and this water, so sorry, I circled the water first. So the CO2 that we have on the left and the water, before they broke down to that, they first form H2CO3, and this carbonic acid broke into water and CO2. Okay? Try at home to predict the product of the double replacement reaction between HCl and calcium carbonate, and you will see that the first products that you guys have are going to be H2CO3 and CaCl2. Then the decomposition portion of this will be when H2CO3 turns into water and CO2. Acids and hydroxides also react with one another, and when this happens, this is called the neutralization reaction. Every time we have a neutralization reaction, the products will always be a salt and water. In these reactions, this is also an example of double replacement reactions.